Hello everyone, my name is Danielle Abruzzo. Thank you for choosing to listen about my final project. Today I'll be walking you through my case study in security monitoring. The problem statement I defined at the beginning of the project was, given a set of features measuring activities in a local area network, could we use machine learning algorithms to predict the type of connection? In other words, to differentiate normal network connections from attacks or intrusions. And the ultimate objective is to explore how big data technologies can be used to detect these intrusions before they impact system performance. The data we'll be using for this project were originally prepared by MIT Lincoln Labs in 1998 for an intrusion detection evaluation program. And then they were used for the KDD Cup in 1999, which is an international knowledge discovery and data mining competition. I obtained this data set from the UCI machine learning repository. So a little bit of background on this data set. There are about 5 million observations and 42 quantitative and qualitative features describing network connections. So the way these data were prepared were that MIT Lincoln Labs set up a local area network, or LAN, which is typical of what you would see in a US Air Force. And they operated connections in this network over several weeks. They treated the environment as if it were a true military network, but they occasionally blasted it with multiple attacks of various types from predefined probability distributions. And over the course of performing these simulations, they recorded network activities such as length of connection, number of data bytes sent, number of failed login attempts. And here we're defining a connection as the flow of data between a specific source IP address and a specific target IP address over some well-defined period of time. These data are labeled with the class of the connection, so either normal or one of 22 distinct attack types. For our purposes, we will treat this problem as a binary classification problem. In other words, we don't care what kind of attack it was, but we're really just interested in distinguishing normal connections from any sort of anomalous connection or attack. The tool we'll use to investigate this problem is SparkML. This tool was introduced in lecture. So again, to summarize what this tool does, it's a data frame-based API that supports a variety of machine learning algorithms for regression, classification, and clustering. It's convenient in that it provides functions for transforming raw data, training models, and evaluating predictions. And all of these different steps of the machine learning process can be combined into a pipeline, which can be used to create workflows and ultimately speed up the process when the same set of rules is being applied over and over again. However, one downside of SparkML is that it currently supports fewer algorithms than the original RDD-based API, SparkML-lib, but I'm guessing that as SparkML becomes more mature, there will be many of the algorithms that were implemented in SparkML-lib will also be implemented in SparkML. From the SparkML API, I chose two machine learning algorithms to use on the network intrusion data. The first one is Decision Tree Classifier, which builds decision trees for classification. And the second one is GPT Classifier, which builds gradient boosted decision trees for classification. In general, decision trees are more friendly and interpretable models for classification than logistic regression because they build trees of decisions to follow for each observation at prediction time. But one downside of decision trees is that the models tend to overfit on the training data because you can have many breakpoints to make various decisions, and the tree can become dependent on relationships found in the training set. One way to alleviate this overfitting is to use an ensemble approach, such as gradient boosting. Ensemble methods train multiple trees on various subsets of the data, and then combine them to optimize performance. Gradient boosting, in particular, produces an iterative network of trees, with each subsequent tree predicting the error of the tree before it. And then those predictions of the individual trees are combined to produce an overall model prediction. GBT classifier, in particular, does this by tuning each iteration on the training set to place more emphasis on poorly predicted observations from prior iterations. Now we'll talk a little bit more about decision tree classifiers in particular. So this feature has some pros and cons. A pro is that it supports decision trees for both binary and multi-class classification, and you can use both continuous and categorical variables in this model. It's also fast and efficient, partitions data by rows, so it allows for training of models with millions of observations, which was good in my scenario because the dataset had 5 million observations. A con, though, of this feature is that the user cannot specify a specific decision boundary for classification. Spark uses 0.5, so if you had a certain scenario where you wanted to make the boundary 0.1 because one class you know for a fact is much less likely than the other, that's not possible here. Another big drawback of the decision tree classifier is that it lacks a functionality to output a code-based set of rules to view the decision tree. This was a feature that was present in Spark MLlib, so hopefully they will bring this back for Spark ML. Here I list some of the model hyperparameters and the model outputs. So the model hyperparameters are max depth, max bins, impurity, min info gain, and min instance per node. So all of these hyperparameters control the size of the tree, how it splits at various decision points, what information is required for splitting. And those hyperparameters can be explored in detail and used to avoid overfitting. The model outputs are prediction, raw prediction, and probability. Prediction and probability being the most important. So prediction is the actual class prediction. So was it 0 or 1? In this case, a normal network connection or an attack. And the probability is the probability that the model assigns to that observation being one class versus the other. So this is what I was talking about with the decision boundary. If it's less than 0.5, then that particular observation will be assigned to one class, and if the probability is greater than 0.5, that observation will be assigned to the other class. Now we'll move on to gradient boosted decision trees. So this particular feature in Spark just says normal decision trees can be trained on datasets with millions of observations. However, this feature is much less mature than the decision tree classifier because it currently only supports binary classification. So we cannot use multi-class classification here, and the model only has one output, which is prediction. So this severely limits what the user can study from the model. And then in addition to the model hyperparameters available for decision tree classifiers, we also have loss type, max number of iterations, and step size. And again, these allow the user to control how much the model fits the training data. Now we'll actually demonstrate how these models were trained and actually how they perform. So after transforming our data set, we train the decision tree model, and the resulting model has depth 5 with 47 nodes. On the training set, we can identify the predictions that the model makes, and as we can see in the table on the bottom, it correctly predicts over 3 million of the observations in the training set, and only incorrectly predicts less than 4,000. So this is a model accuracy of over 99% on the training set. However, we might worry that the model overfit the training set. After training the model on the training set, We can then run the model on the test set and again evaluate its performance. We use a transformer to make predictions on the test set and then make a confusion matrix of sorts to again evaluate how many predictions were correct. But still the model is over 99% accurate. That's pretty amazing considering that we've built a standard decision tree model with all the default parameters available in Spark. We can also look at the model's sensitivity and specificity, which is nicely described by a ROC curve. The area under the ROC curve is almost 1, which is nearly a perfect measure. We can also have a visual of the ROC curve. As you can see, the ROC curve has a near 90-degree angle, which indicates extremely strong model performance. So it has a very low false positive rate and a very high true positive rate. You rarely see ROC curves with this shape. The other summary we can show for this set is a violin plot. So the violin plot functions as a continuous visual of a confusion matrix. And as you can see in the plot below, we have two classes, anomalous connections and normal connections. And what we've plotted here are the probabilities of observations belonging to each one of these classes. So you see an extremely wide separation here between the probabilities in the normal class and the probabilities in the anomalous class, which means that this model very accurately predicts connection class and can distinguish between these two classes. And the dots you see on this plot are the outliers. So we'll occasionally have, for example, an observation that where the model output almost 100% probability of it belonging to one class, which in this case would correspond to anomalous, but the observation actually belonged to a normal connection. We can also view feature importances for this model. The vector below gives us feature weights by column number, and these weights indicate the feature's relative importance for predicting connection type in this model. And as you can see, by far, the feature with the most importance in this model is count, which measures the number of connections to the same host as the current connection in the past 2 seconds. The weight on this feature is about 0.88, and you'll notice that the next largest weight is only about 0.08. Now we'll show the implementation of the gradient boosted decision tree for classifying network connections. So we train the gradient boosted model on the same training set as before, and we set the maximum iteration to 10, which signifies the number of trees that will then be combined into one. So in other words, the number of trees that will separately predict in different subsets of the data. And we set this max iteration to 10 in hopes of avoiding overfitting. We can, as before, output a table of predictions made on the train set, and still the model is 99.9% accurate on the train set. So notice that this 99.9% accuracy is slightly higher than on the non-ensemble decision tree method, which is expected because gradient boosted decision trees are supposed to be more specialized and improve model performance. Now we can view the results of this model on the test set. As before, we create a confusion matrix of sorts, and as you can see, the accuracy is still extremely high. We also print the area under the ROC curve, which is, again, nearly 1, which is a perfect score. So the important thing to note about this gradient boosted decision tree model is that the GPT classifier in PySpark, as I mentioned before, does not output probabilities. So because of that, we can't make the ROC curve and violin plots that we did for the decision tree model. However, the best we can do here is, again, print a vector of feature importances. And again, you see here that by far the feature with the highest weight for predicting network class is count. You'll notice, however, that the weight on count is now 0.60, whereas for the decision tree model, the non-ensemble approach, the weight was 0.88. So in comparison to the decision tree model, the gradient boosted decision tree model puts much less weight on count. In conclusion, SparkML provides a very limited but user-friendly implementation of decision trees and gradient-boosted decision trees. Given our simulated network connection dataset, it seems very easy to predict attacks using decision trees. Both the standalone and ensembled models were over 99% accurate. So that means in practice, decision trees seem to be a viable solution for detecting anomalies and responding to network intrusions. Hopefully, this sort of technology could be used to identify intrusions before they impact application and system performance. And next steps for taking this project further would be to try unsupervised methods on this data set. And one method we can use for unsupervised learning is clustering. So we could identify the features that are most important for determining connection class and see visually if normal network connections and anomalous network connections cluster together in distinct packets. Another thing we can try for this project is to get maybe different data. I know it's hard to find data that weren't simulated, and that's in part why I think the model accuracies were so high across the board here. But if we could find perhaps a different data set, we could test how decision trees and gradient boosted decision trees perform on those data sets where simulations didn't take place from some sort of predefined probability distribution. So thank you for listening to my presentation. I hope you've learned something here, and have a good night.